Thanks for the opportunity to speak with you today. It's a real treat. Jim and I have been looking forward to this presentation for some time, and I think we have some interesting information and thoughts to share with you today. My name is David Gillespie. I'm an architect with SSOE, and I focus on mission-critical facilities and data centers.
My name is Jim Otte. I'm a member of the SSOE electrical group working specifically in data, fire, and security systems. See a brief introduction and bio on both of us here. We're not going to take the time to read through these. However, this presentation is online if you'd like to scroll through them slide by slide.
This original presentation was done under the AIA requirements for continuing education. The AIA requires that you have learning objectives, which we have on the screen at this time. And now on with the show. All right, here's a slide with just a general timeline that wants to bring you from the ancient Greeks in 3500 with Hephaestus and Pygmalion all the way through the modern world. And some of the highlights along the way, you'll notice that Leonardo da Vinci's robot was conceived in 1495. And you'll hear a lot of interesting names for some of the equipment that we see in the upcoming slide. And Da Vinci is certainly one of the leaders in robotic healthcare. So keep an ear out for some of the interesting names as we go forward. The fundamental concept of robotic technology and telemedicine is a transition from the tissue and instrument to information and energy, and that'll be a concept that we're going to continually come back to throughout the presentation. The healthcare industry, as you know, is probably one of the last major industries that has not truly embraced the digital or data technology. The healthcare industry is one of the last industries that has not truly embraced data technologies. We are definitely behind, and we're struggling to catch up.
And Dave, one of the things that strikes me is when you look at manufacturing facilities and you look at their automated production, just-in-time ordering, it's really come to fruition in the manufacturing and commercial type arena, but it hasn't happened in healthcare industry. And I think that we're starting to see the advent of automation and processing systems starting to be integrated into the healthcare arena, not to the aspect of becoming a robot type hospital, but the ultimate destination or the ultimate conclusion is improving the quality and level of care and also reducing costs to the patients. And I think everybody will see that a little bit more as we go through the presentation.
Modern history of the healthcare robots and the medical robots starts really in 1985 with the first medical use being a Puma 560. That machine was used to do medical biopsies in a neurosurgical environment. Healthcare robots, we're really going to start with the word robot itself, which was a word coined by a Czech writer named Karel Kupik in 1921. And it's really derived from a word that in Czech means forced labor. And I realized that a lot of the nurses in hospitals might think that applies to them. But in this case, we're talking about medical robots. The first medical use was in neurosurgical biopsies. It was 1985, and it was the Puma 560. And it goes through the timeline of some of the different ones, goes through the Robodoc, the ESOP, and all of the ones that bring us up to 2010. And then 2010, that was the first truly robotic surgery. And by robotic surgery, we mean instructions were given to the robot, and this was not an extension of the surgeon's hand. This was actually a surgery performed under the complete instructions that were previously entered into the system. The global robotic market right now is at approximately $1 billion, and estimates are that it'll grow to $5 billion by 2015. And that would represent approximately 6,000 robotic surgical systems placed across the country. The Journal of Obstetrics and Gynecology conducted a survey of robots used in their soft tissue prostatectomies and hysterectomies. A total of 432 hospitals were identified, and of those, 44% advertised the use of robotic devices in their hysterectomies on their website. This number is in line with other studies. Robotic surgical market size is currently $1 billion, and it's estimated to grow to $5 billion in 2015. That would represent a total placement of approximately 6,000 robotic surgical systems. Hospitals have often been thought of as centers of information. The infrastructure to support that going forward needs to be in place right now. In today's discussion, we're going to talk about robotic applications in the hospitals in the following areas: surgical, physical therapy, bionics and prosthetics, caregivers, simulators, pharmacy, and logistics. And as we go through all of these, we're going to be discussing the implications on the hospital and the implications on the infrastructure that needs to be in place to support all of these various technologies.
And I think it's interesting that almost 50% of the prostatectomies that are done in the United States today are done by robots, and almost 1/3 of the hospitals currently have some type of robotic technology in place within the hospital environment.
I don't know how many of you may have seen the news a couple of weeks ago, but there was a gentleman named Zach Bauder who climbed 103 flights of the Chicago Willis Tower with a thought-controlled bionic leg. And you can see in the picture there, that is a truly bionic leg with micromotors, servos, and all of that was controlled through a biofeedback application that was wrapped around his upper thigh. And it was pretty exciting to see this. This, again, is coming through some of the Department of Defense and medical military spending. So you're seeing some real bionics out there, and it's not just TV in Hollywood. We did an overlay of the various applications that we just showed on the previous slide. And what we're seeing, and this is market growth reported by the various industries, and we're seeing an uptake in every single robotic area. And the one that you'll see that has the steepest curve is in the physical therapy. And we'll discuss that a little bit later, but that one is a real outgrowth of all of the innovation that the Department of Defense and the military and the VA has been putting into the rehabilitation. And all of that is as a result of the Department of Defense and the VA putting money into the care and the rehabilitation of the wounded warriors and the soldiers coming back from the various theaters of war across the world. And here's another slide just giving you an idea of how we've been progressing from analog to robotic in the procedures that Jim was just mentioning. This is from the Da Vinci Corporation, it's Innovation Systems, and it talks about the growth of robotic procedures in the prostatectomy. You can see on the slide that in 2010, we were over 55% of the procedures. It's leveled off a little bit, but we're anticipating this to continue to grow. The robotic procedures, taking the analog systems and advancing those forward is on an upward trend across the board.
And what you see on your screen right now is an actual picture of the Da Vinci system. The doctor is positioned in a very ergonomic position, as well as the physical assistant who's overlooking the patient. To your very right, you can see the physical robotic arms that do the actual surgery on the individual patient. The costs for a Da Vinci robot are typically between $1 million to $2 million. Now, while a lot of people will consider that to be somewhat expensive, costs have come down significantly. And as more of these devices are put in place in hospitals, you'll see costs continue to decline. Maintenance costs typically are around $150,000 annually. And some people will ask, well, what does that equate to in the individual cost per surgery? And we'll talk about that a little bit later on. As far as the numbers of surgeries that are occurring, in 2010, there was 220,000 robotic-assisted surgeries, and in 2011, there was 360. So that number comparison alone tells you that robotic surgery is growing tremendously. A breakdown of the actual types of surgeries that are occurring is shown on the right-hand side of the screen. When you look at cost comparisons of robotic surgery versus laparoscopic surgery, open-type surgery for prostate removals, you'll see that robotic surgery is a little bit more expensive. However, some of the advantages is less recovery time and other issues, as we'll get into in upcoming slides. Kidney removal also is shown there, the cost comparison, the differences between robotic, laparoscopic, and open surgery. When you compare the advantages or the different types of operations, laparoscopic, open, and robotic surgery, you'll see a number of things that are advantageous to the patient. There's decreased blood loss, there's reduced recovery time, major and minor types of complications are reduced significantly. The urinary functions return to normal conditions quite a bit more effectively, and sexual functions return faster than under other types of surgeries. So with those advantages basically in place, facilities are seeing that the advantages outweigh the additional cost of $1,000 to $1,400 per surgery. when you look at surgery today and now in the future, most of your surgeries are based in urology, prostates, and gynecology, hysterectomies. However, when you look at in the future, you're going to see more ear, nose, and throat, more thoracic type surgery, and more types of general surgery, including heart. Some of the advantages that the Da Vinci system offers and other robotic technologies is that the system provides true life 3D vision, enhanced dexterity, superior ergonomics. The actual doctor gets less tired because of his particular posture that he's able to maintain throughout the surgery, less blood loss, a smaller incision size, etc. What the patient sees are shorter hospitalization stays, reduced pain, faster recovery times, and smaller incisions, which causes less pain over time. Hospitals, the advantages are increased efficiency, reduced costs, less likelihood for litigation, and it's also a marketing tool that a lot of hospitals are using to attract more patients. Some of the disadvantages that robotic surgery has is that it has a high purchase maintenance cost. There's a high initial cost that has to be benefited over time. So there is quite a bit of a cash outlay at the inception of the purchase. It requires a cultural shift in the hospital. David, as you're aware, it allows the nurses and the doctors, they have to prepare more for surgery. It takes a little bit longer time for them to get post-op preparation in the operating room to be able to customize the robotic to that particular type of surgery. And because of training times, there are steep learning curves that are involved. However, I will tell you that I had the opportunity to actually do a simulated prostate removal with a Da Vinci, and they gave me a B-, which I thought was pretty good for myself. And I thought if I could perform a surgery with limited blood loss, probably anybody could. But the point is not the ease of it. The doctors need to be able to be trained as to adverse effects. Do the lights go off in the operating room? Is there a complication involved? Is the patient suffering a heart attack while the surgery is occurring? Those are the types of training things that really take the time to be able to prepare with how to take into account those other complications while the surgery is being performed. What you're seeing here is a close-up of the actual tools on the Da Vinci. And there are a number of different hands that can be positioned. There's also a camera that can be inserted into the body that aids more 3D visualization, as you can see in the top right-hand side. And we talked about that superior ergonomics. The slide on the little image on the lower right-hand side shows you the hand positioning of the Da Vinci system, which allows you to manipulate different organs and different tools as needed. And it is quite comfortable. We talked a lot about Da Vinci, but there are also other robots that are out there in the industry today. Here's an example of a cyberknife. A cyberknife is a radioactive type of device that can actually take the radiation into a laser beam and shoot it actually into the tumor. While the tumor is being radiated, the cyberknife looks at the size, position, and density of the tumor and is able to make minute adjustments during the radiation. It's also be able to take the radiation and direct radiation from all sides of the body 360 degrees, which allows you to take small pulses of radiation, and it has less problems with tissues that are surrounding that tumor because of the directed array that they use to be able to direct that radiation. One of the advancements that's happening from the military type intervention, military type surgeries, is the Raven. The Raven is a fairly easy to set up. I call it a, David, you had equated it to a fancy erector set at one point in time.
Yeah, it's like an erector set on steroids. It has some amazing opportunities and it's open source. I think Jim can talk directly to the advantages of open source and why we are encouraging more development in this area.
Right. The Da Vinci system has its own proprietary software package. Because of its complexity, it's not able to be easily modified and interfaced to other applications. The Raven is an open-sourced application, so you're able to tie in third-party type applications to surgery devices. And as everybody knows today out there in the industry, things that are open source tend to have a better stay and better growth record than things that are proprietary. Here's a picture of an Amadeus type robot. It's coming out there in the future. It's due to be injected into clinical trials in 2013 and have FDA approval, if all goes well, by 2014. The Amadeus system has specific advantages over the Da Vinci system in a lot of different areas. It's smaller, portable, and they're touting it as less costly than Amadeus. So when we talked before about overall robotic surgery costs lowering, this is going to be a key motivator for robotic technologies to reduce costs. One of the things that I see as being a really strong advantage in robotic technology is devices that can operate on the beating heart. Right now when somebody goes into surgery, they literally have to stop the heart, put on the heart-lung machine. These particular devices have the capability to operate on the heart while it's beating. Because of its capability to actually change and pulse with the beating of the heart, they can do surgery like the implanting of stents and removal of specific masses on the heart without having to shut the heart down. Less recovery time, less pain. You don't have to open up the chest cavity, detach the rib cage, etc. One exciting advancement when you're talking about stent, the placement of stents into hearts is the Cornelius system. It just recently got approved in July of 2012 for general type surgery. This is a device that has a snake type system that is able to go through the heart's arteries and put stents in place, allowing for a lot less incision size and a lot faster recovery times. We've been doing a lot of talking about large type robotic systems. As everybody, if people have been in the operating room as well, they've seen there's a lot of hand type assist type robots that are small in fashion, not necessarily a lot of electronic control or computer interfaces, but it allows surgeons to do things and make sure that their hand is stable, less tremor, other types of effects. So I just didn't want to discount when we're talking about robotic technology about those small appliances.
And really what you're talking about is you're taking that surgeon and pushing them forward and advancing their ability to treat and to react to the surgical conditions. One way the military has pushed that even further is with their LSTAT unit, which is the life support, trauma, and transport. And that's the gurney that you see on the left-hand side. It's not just a little pair of sticks and some canvas anymore. The corpsmen have these in the back of a Humvee in a forward position during a military engagement. And what you see is a complete patient support system with monitoring, control, IV pumps, fluids, respiration, all of the vital signs, and all of that is completely underneath the patient from the point at which they are taken from that trauma, the insult site, and put on that. Then that is then transported back to an aid station or further back to a hospital. And what you'll see in the bottom right slide is that same LSTAT unit is underneath the operating table. It's actually the operating table where you've got robotic-assisted devices over the patient. The ability to rapidly transport the patient and to maintain a consistent stream of data for the surgeon is life-saving. And what we're finding is that these things are reducing the fatalities in that golden hour that most people might be familiar with. So what we're seeing here is a real high-tech stretcher that has advanced us into the technological age. And again, this is all advancing the doctor's reach and the surgeon's reach out into the field. The corollary to the advancements in the medical devices and the medical systems in the military is the returning soldiers and the impact that they've had on physical therapy. The physical therapy world has just exploded by leaps and bounds with all of the robotic assist equipment that's out there. You're seeing a young man here on the left that is learning a walking gait technique with robotic assist. He is a CP patient, and he has advanced advanced from being completely chair-bound to now he's able to walk with crutches, and the goal is to see him up and walking on his own in the very near future. All of this is possible with the robotic technology that's able to record the range of motion, the strength of a muscle group, the flexibility of a muscle group, and repeat that over and over. And instead of having a physical therapist check their notes every time when they're working with a PT patient, they can go back to the data log and see how that patient has been responding over time. On the right, you'll see an occupational therapy setup where a repetitive motion injury is being rehabilitated through the use of a robotic interface and a wrist manipulator. The next step after some of the physical therapy, when the actual limb is no longer available or the organ is no longer viable, is the replacement. And we're talking about limbs and organs, and these are the prosthetics that we see with the limbs. And in the center is the Jarvik heart. I think it was the Jarvik 6 heart that was transplanted into Barney Clark. I think we all remember that from the late 80s. Zach Botter's leg is the one on the bottom right. It's a better close-up of his bionic leg. They won't release the price tag on that, but the overall system cost to date has been $8 million. So that's probably half of that is in the cost of the micro engineering that's gone into that leg. One of the next systems of robotics that we're seeing in healthcare is the caregiver. This is the patient interaction, the two-way, the sort of the FaceTime opportunities that we're seeing in the telemedicine world. What you have is the ability for a doctor or a caregiver to advance or push themselves out in a virtual sense to the point of care. On the right, you're seeing a caregiver giving a simple examination to a patient where the doctor is online and he's seeing the same telemetry stream that they would be in the room. And what this allows to have happen is that it allows doctors who may be a particular specialist in a location to push themselves out into a community that may be 200 or 300 miles remote from their location. And a consult for a physician with a world-class specialist is no more than 10 to 15 minutes, where in the real world, you're talking about taking someone out of their specialty for maybe a day and a half to visit a single patient. This allows those specialists to see many more patients and to leverage their education and training across the board. And I think Jim has a real personal example of how telemedicine affected his life.
Right. One of the things that I found astounding, Dave, when we got more and more into hospitals, I'm an electronics guy, was the percentage of improvement that the right lighting conditions, that the right type of sound levels can aid in a patient's recovery time. And even more than that is patient interaction with family members. My mom was in a nursing home for a number of years, and she took great joy in a connection that I provided between herself and a number of relatives. So she was able to video conference between myself and her other siblings as well as her daughters, and be able to interact them on a daily basis. And that visual attention to be able to see the person rather than just talking to them over the voice was very reassuring to her. We could also gauge her current conditions, make sure that she was doing well, etc. And it was almost like us being there. You see the caregiver that's on the screen right there by iRobot. Certain hospitals are also allowing patients to have these scheduled in the room. So if you're a daughter or a son, you can schedule the iRobot after hours when the doctors are not making rounds and have this iRobot visit the patient and have an interactive conversation with them, just kind of like you were standing there but it's just over video.
I think one of the other robotic systems that we're seeing come into play right now is really sort of a Hollywood. It's pretty high tech. These are the simulators, and these are simulators that allow physicians and caregivers to practice procedures and practice their craft in a situation that's not life threatening. In the very beginnings of medicine, it was always done with cadavers and bodies, and students had to learn on dead tissue. What they've done now with some of these amazing robots is they have respiration systems, circulatory systems, nervous systems, and so all of these things can be simulated, and as the patient simulator is there on the table, they can interject from a remote location various scenarios so that doctor can get used to the unusual things that may happen during the course of a particular procedure. You see a delivery mannequin up on the upper right, and then down on the lower, you're seeing some of the neonatal care. I think anybody who's been through these neonatal intensive care units some of these children are being weighed by the grams, and when you're holding a single human life in your hand, you can tell quite readily that all of the things that need to be applied to that for an adult patient would weigh more than the actual baby that's laying in that crib or in that bassinet. So they need to practice, and they need to understand how to place the monitors and the tubes and the IV leads so that they give that child the greatest opportunity for a healthy life. And these robotic surrogates or these robotic mannequins are an amazing addition to the arsenal of teaching tools that most hospitals have available. Here's another installation, or here's another instance where simulators are coming in. This is a 3D simulation that's much more of the video generation than the surrogates or the mannequins. This is stereoscopic goggles that the doctor can put on and view the patient. And on the left, you can see a carpal tunnel surgery being performed in a virtual world where that doctor can practice over and over again in a true stereoscopic 3D visualization. On the right, you're seeing a heart, I believe that's a heart organ transplant going on, and all of the sutures and the clamps and everything that's available to that surgeon is available in this 3D simulation. The doctors that are running the simulation can also, again, like with the surrogate, they can interject a heart attack or a bleeding vessel or things of that nature. So they can really throw a lot of things at the surgeons and the care teams to practice before they get into the OR. A good friend of mine from college is a liver transplant specialist in Atlanta, Georgia, and they typically run 2 complete AV scenarios before they'll do a live transplant, meaning that they'll go through with the entire team and they'll do the transplant 2 times in the virtual world before they actually go in, because liver transplants are so delicate and so tricky, they just can't take the risk of any unknowns or any gotchas when they get into the surgical suite.
One of the exciting things, we talked a lot about surgery and operations. However, one of the things I'm most excited about is cost reduction in hospitals. And examples that's being showed on the screen right now are pharmacy compounding and dispensing type operations. Currently, they say that 1/3 of hospitals have some type of robot or automated medication processing system. I think that number is a little bit high. However, when hospitals do put these systems in place, they see a number of advantages. Dispensing accuracy is improved up to 99%. Cart fill labor is reduced by 72%. So you don't have to have that cart going down to the pharmacy, having it returned to the patient, and having that physical transfer of information. And then also, the cost reductions can be in the $2 million range of savings, and we'll talk a little bit more about how that occurs. Here's an actual example. St. Joseph Hospital in Savannah, Georgia, they installed an IV station, and basically what the IV station does is it creates IV bags. A lot of hospitals typically today have to order out IV bags and bring them in specifically for that patient. Well, all an IV bag is a diluted medicine in a bag, basically with saline solution. The IV stations are able to take these saline bags, put the actual undiluted chemical into the bag to the concentration required, and basically create their own IV bag on site. St. Joseph Hospital reduced their yearly IV costs by $233,000. And Chandler Hospital, who used to pay $6 for 1 dose of medication in an IV bag, has now reduced that medication dosage costs to $2.32. So there's quite a bit of savings. Another example of robotic technology and how it's being integrated into the hospital is what I would call tugs. These are automated robots and delivery type systems. And they're basically used to deliver pharmaceuticals, deliver food trays, deliver blankets, and also waste disposal type systems. These robots are self-controlled. They have GPS capability. They don't run over people, as some people say. If they bump into an individual, they'll say, "Please excuse me, I'm trying to get around to you." Not only are they cost effective, but they're also very polite. And what you see here is an image of a tug that has been decorated for a children's pediatric unit to make it a little bit more friendly in those types of arrangements. El Camino Hospital in California's Silicon Valley, they were building a new $470 million facility. They purchased 19 tugs, basically to provide deliveries from laboratory and pharmacy, materials management, basically waste removal, and dietary and environmental services, blankets, and also food trays. In the first year alone, they saved $650,000 in staffing expenses. Now, this was not a staff reduction type program. When they put these robots in place, they saw their patient satisfaction rates improve dramatically, basically because these nurses were able to do what they were there for rather than running down around the hospital, taking garbage out or delivering blankets to patients. These devices were automatically delivering these types of products to the respective patients. So the satisfaction rates improved quite substantially.
On the picture on the left, you'll see a couple of hospital administrators walking through a sea of tugs, so to speak. It's kind of an example, and the tugs are running around $30,000 a piece, and so you could see how quickly you could recover that cost. And I think Jim talked about materials management. I think one of the things that a lot of hospitals struggle with is the soiled materials removal, sharps and contaminated bio waste and biohazards. Most of the biohazards that are in a hospital are in certain closets, and those closets can be equipped with a camera and an outfitted. What I'm trying to get to is that it's an automated request for the tug. In hospitals that are using tugs for biomedical waste removal, each of those rooms, the waste rooms, the hot waste rooms, have a device that allows those tugs to be alerted when there is biohazard waste to be removed, and they automatically are deployed. So it really reduces the interface time, and these robots are doing some amazing things all on their own. So they're not required a great deal of control. They have a program, and they run through their program on a daily basis, and we're seeing a real opportunity to return caregivers to the patient bedside and not walking up and down the hall with carts and trays and blankets.
I'm sure everybody's seen the television programs where they've taken these vessels and put people inside of them and reduced them down to a very micro-miniature size and basically injected them into a body to remove a particular type of abnormality or a cancer. That type of technology is being created, but it's through micro-miniaturization of electronics and nanotechnology. And you don't have to have people inside these. They're self-automated. Basically, they're able to navigate through blood into arteries, go to areas where there might be plaque or other types of abnormalities, and perform surgeries in those areas. Now, this is not current technology. This is something that is probably going to happen within the next 10 years as nanotechnology advances. Something that's a little bit closer on the bottom left-hand side of the screen, you see that little white object that's in the palm. That's actually a device that can be implanted inside of a person with blood sugar level issues, and it will actually measure inside of the body a person's blood sugar, so they won't have to constantly prick their fingers for measurement of the sugar levels in their body. They can take their iPhone or their Android phone, and this little device inside the body will transmit their sugar levels to their iPhone on a regular basis, which allows them to get better indications of what they're eating, their exercise levels, and things of that nature. The middle, you'll see a bionic arm that is being tested. Probably will be out in clinical trials within 10 years. Will allow people a lot more dexterity. These types of devices are being attached to thought centers and thought areas of the brain so that they do have some type of capabilities for communication other than voice. So by sending certain brain signals, they'll be able to move their arm. On the top right-hand image, you'll see a small, tiny little device that can be implanted inside organs, livers, or lungs to monitor contaminants within the body as well as oxygen levels.
And here we've come all the way back around to the very beginning of the presentation, and that is, what is the implication to the IT center, to the network, to the infrastructure, to the bandwidth, to the cabling? All of these robotic systems have one thing in common, that is an increased data flow. We've got a lot of information that's now flowing back and forth between the caregivers and the electronic medical record and the individual devices. And the gold standard that we're all trying to achieve is the highest bandwidth, the greatest connectivity with the highest safety and security. And that's the typical challenge that Jim and I face on a regular basis. We have to make sure that all of the infrastructure is in place to allow these caregivers to provide these services anywhere, at any time, on any device. And I think that goes to the very heart of what we're talking about in our discussion with robotics and the impact in healthcare. Comfort and control, efficiency, patient satisfaction, and recovery times are all the result of these infrastructures being in place. The slide on the upper right is not too far from the reality. Jim and I visit a lot of data centers and hospitals, and the thing that we see over and over again is that those data centers are overburdened. Their cabling infrastructure is what we call legacy, and that's a nice way of saying old. Some of the systems that we see are not well managed, not well maintained. The future that we'd love to see is something on the bottom right, and we realize that's the goal that we have every time we walk into a hospital. So what we want to do is make sure that the implications for all of the medical technology that is growing and going forward is going to be able to be handled and live on this IT infrastructure and network that we're putting in place.
And it's especially even more poignant when you think about the fact that the static connectivity are actually communicating life-type messages. In other words, with Da Vinci, what is happening to overcome that training issue that we talked about is that a doctor in California can be supervising an operation that's being performed by a doctor in New York. So when you're talking about these data connectivity issues, it's really important that somebody just don't unplug a cable at some point in time and misunderstand that you see the gentleman crawling under the inside that IT cabinet. It's a very dangerous thing. It's very important to make sure that you know what the cable is for, what it's used for, but also to make sure that it's the right size to convey the information that is necessary.
And one of the things that we see over and over again, and Jim and I were at a presentation recently talking about bandwidth and talking about cables and getting down into the real deep details. And here's a real simple example. Many of the hospitals we visit on a regular basis have a 10 megabyte or a 100 megabyte backbone in the cabling system. Well, here's an example. We have a CAT scan. A typical CAT scan is about 500 images. On a 10 megabyte backbone system that's out there right now in hospitals across the country, to transfer that entire CAT scan is going to take about 8 minutes, 65 seconds. 8 minutes, 65 seconds for a CAT scan to reach its intended designation. Here, we can jump up to the 100 megabyte, and we've cut that time down in half. It's 4.5 minutes when we're using 100 megabyte. You can see where we're going with this, because you may have a surgeon in an operating suite who needs to see the most accurate, most timely CAT scan. That surgeon is performing an operation, and they're going to have to wait for that image to be delivered. When we get to the 1 gigabyte backbone, which we're seeing in some hospitals, we've gotten that time transfer rate down to 2.2 minutes. Where Jim and I are hoping to advance our healthcare clients is to move into the 10 gigabit world, where you're looking at less than 30 seconds for that 500 image CAT scan to be delivered into the operating room, where that surgeon or that physician has the patient opened up. And I don't know that there's any better example of what we're trying to do and how we're trying to translate bandwidth into the saving of life, into the advancement of care.
EMR adoption is being mandated by the government and already in the healthcare industry. The stages of implementation are very challenging to organizations, to the point where the government has actually delayed certain stages of EMR adoption, basically because of a lot of connectivity issues that are happening out there in the industry today, as well as other patient records issues and the ability to be able to adopt this new infrastructure and this new system. So one of the things that hospitals need to look at as they're transitioning to an EMR system is to make sure that their data infrastructure within their hospital will meet the requirements of their EMR record system. These EMR systems contain a lot of images, and as David just explained, these images take a while to transition through the network. Dave and myself joke a lot because I'm an engineer and Dave's an architect. And when we think about the patient rooms, Dave thinks about a patient room to look something like this. There's no obstructions. Everything's.
I kind of like that.
Yeah, exactly. This is a BIM model of a patient room. For Dave, it's a very sterile environment, and that's what he looks at. Look, there's no plugs on the wall. There's no IV bags. When I think about it, I generally think of a worst case scenario, something at the order of this, where you have to look at how the patient room is going to need to be adapted in a worst case scenario. And typically what happens in an application when they need to add data jacks is that they will close down a wing of a patient area and add data jacks into the wall, because whenever they need to cut into drywall, they need to close that room down. Well, if you put systems in that are adaptable, you're able to eliminate those types of issues. And here's an example of some of the facilities that we worked in where we kind of looked forward future and created a wall type application where jacks can be mounted in a tray, basically where they can be moved side to side and adapted as necessary. These types of applications also can include gas supply type systems, and jacks are able to be added or removed as needed and without having to shut down the wing of a hospital. And I like the approach either also where you can tie in lighting into these types of applications so you don't get that direct light that is very offensive to a lot of patients in the recovery mode.
And I think what we're seeing here, Jim, is that we're seeing an arms race, not just in the medical equipment, the big MRI, CAT scan, and robotic systems. We're also seeing an arms race in the patient care interface. And I think that's the one that gets us all so very excited, because most of the time that you're in a hospital, you're not in the operating room. That takes up only 5 to 8% of the time that you're in that facility. The bulk of the time you're spent in the hospital bed, and you're dealing with all of the systems and all of the services that are being brought to you. I think we can all agree that the head wall that you see in those two images is much cleaner than the image of the gentleman in the previous slide. All of that has to be taken care of and has to be planned ahead of time. And I think that's what Jim was talking about before when he was talking about trying to future plan these hospitals. And getting to the point at which we have the capacity to grow regardless of the need and regardless of the future requirements. For example, the patient bed that you see here may be on a pediatric wing for a period of time, and then later on needs to be converted to a step-down unit from a surgical care system. It may need to later on go into an orthopedic or a pediatric. With all of the modular components that are in that head wall, that room can continually evolve to serve a variety of patient needs without having to shut down the wing or shut down that room to repurpose that room. And that's exciting to us.
And what you see on the bottom of the screen there is basically a typical example of how we design a jack-type configuration in a head wall. They don't necessarily have to be all together, but you need to plan for the future and plan for spare devices that are going to be connected as EKG machines, as blood pressure monitors start to get more and more enabled and start getting tied into these EMR systems. What you're currently, a lot of hospitals still maintain large inventories of paper records, and they're starting to transition between the paper record system and EMR. As this transition occurs, security levels for this paper storage still has to be kept in place for the required period of time. But electronic records are more secure than paper records because they physically take up less space and they're harder to get access to. There are breaches that are occurring in patient electronic records and in paper records, but when you look at the types of requirements or the types of thefts that are occurring, primarily they're internal. And I have a little graph here that's peeking inside of thefts. Most of these thefts or data breaches are occurring by in-house staff getting access to patient information, allowing a contractor maybe who shouldn't have access to a data room to plug a device into a router where he gets beyond the firewall, or an individual who shouldn't have access to all the patient records across the board taking their laptop and copying records. Because what happens is that information is very valuable because it can be sold for identities which people can then use to get credit cards and other other means of financial. What you're seeing on the screen right now is a access control card that a lot of people use to gain access to their facilities. Typically what we do is we give this presentation live, and I ask by a show of hands how many people use this type of technology, and about 90% of the individuals raise their hands. When I ask them how many of the people currently with their hands raised know that 90% of the credentials that are out there in the industry today can be easily cloned, only 10% typically know that 90% that these cards can be cloned. In fact, it's very easy. By taking a circuit that has been invented by some students. You see at the top of your screen there is a credential that is used by a bunch of individuals, typically to gain access to a facility. And typically when I'm giving this presentation live, and I ask for people to raise their hand if they use this type of credential. I'm always surprised because typically 90% of the people out there in the audience raise their hands. I ask them to keep their hands up and to lower their hands if they are aware of the fact that these credentials are easily duplicated or cloned. And typically 10% of the audience is aware. The other 80% or of the 10% of the 90% is not aware that these cards can be cloned. A bunch of very innovative students at MIT created a small circuit board that you can basically manufacture for $35, and it allows you the capability to clone cards if you get within 10 feet of an individual with a credential. So what I'm able to do with this particular device, and I've actually built one and it does work, is if you get within 10 feet of an individual, you're able to copy their card and then go through the facility as if you're that particular individual. So it's a very easy thing to do. It's just requires a little bit of soldering, and pretty much anybody can make one.
But Jim, I can't solder, and I don't understand how to follow a schematic diagram.
Well,
what could I do to clone a card?
I'm glad somebody asked that question, because you too can have one of these devices without the manufacturing process. In fact, they sell these over the internet for about $40. If you know where to get one of these, you can purchase it and basically copy people's cards or clone people's cards very easily and efficiently.
The link to that website will not be part of this presentation.
That is very true, Dave.
And as we've talked about, from all of the systems from the very beginning, it all comes back to a central point, and that central point is the data center. And in a lot of cases, hospitals are being challenged with whether or not they're data centers or if they're caregiving centers. And we've seen a real interest in hospitals migrating their care centers and their data centers apart from each other. The increasing use of all of the different robotic systems we talked about, and we've said it a few times before, is that it's an increased pressure on the infrastructure, it's increased storage in the data, and it's an increased bandwidth requirement on the infrastructure and the cabling throughout. Facilities need to be prepared not just for the robots, but for the EMR records, for the increased security, for all of the systems that are in the hospital, from an infant abduction to voice over IP to code blue. All of these things come back to that data center, and that's really the brains of the whole system. And Jim and I spend quite a lot of time in the data centers, but we also spend a fair amount of time walking the hospital with the caregivers and the administration to find out what their challenges and their points of pain are when it comes to IT. The thing that we try to do is we try to push the technology as close to the point of care as we can, because it allows us to get the greatest speed, the greatest reliability, and the greatest security.
So with that in mind, what we're asking facilities to do is put together a to-do list of what you need to do in order to bring your facility up to date to be able to handle current EMR type technology and as well as robotic technology. And we're more than happy to be able to assist you with that process. And with that, I myself and Dave Gillespie, we thank you for your time.